much for coming to my talk, especially after lunch. I hope the lunch was not too exhausting for you. So my name is Ignat. I work for Cloudflare, and today we're going to talk about how to protect yourself from the biggest internet threats. So a little bit about myself. I do Linux at Cloudflare. I'm a die-hard Linux fan. That's why I'm presenting from a Mac, and if you can see. But yeah, I just love Linux. I love working on operating systems, infrastructure, security, and performance. And I wanted to reflect on the previous talk with the previous speakers, so like with all these abundance of frameworks. So like, if you're tired of frameworks, come work with us in Linux. For 30 years, it's just like C and an operating system. Nothing changes much. So I do enjoy low-level programming, so Linux kernel drivers, bootloaders, and other stuff written in unsafe, non-managed languages. I was a bit confused about the question from the, like, who uses C++, and I didn't raise my hand, and people said, oh, you're probably using managed languages. No, I don't use C++ because I use C. C++ is just too high level. So yeah. But today we're going to talk about a different framework we all use every day, is the internet. And we begin our story by talking about how various distributed attack on the internet works and how you would protect from them. So let's the first review a simple concept of a denial of service, like not even a distributed denial. So imagine you have a server running like on some infrastructure in the internet, yeah, and you have your users which access your services. What a denial of service means, there comes a malicious user and an attacker, they start sending the traffic to your service and eventually like consuming all resources, overloading it, and then eventually your legitimate users cannot access your service. So what do you do in this case? Well, typical, right? We're all DevOps engineers now, so yeah. Well, we put a firewall in front of the attacker, and for the time being, it kind of like relieves the pressure on our services, and like our users are happy, right? So kind of works. Now let's zoom out of this simple concept and how it works across the internet. So let's see how the distributed denial of service works. So you have the same picture. It kind of works well eventually, but then like more and more attackers or malicious entities come and start sending traffic to your server, and eventually they still overload your server and your firewall, and kind of you end up again having no ability to serve your customers. So what do we do typically in this case? Well, we kind of like hide our server from the internet and put like a bigger firewall in front of it, right? But eventually, more powerful, more expensive, but eventually like more and more attackers come in, like they start sending malicious traffic, and they can still overload your firewall. In this case, they're like, yeah, there is nothing we can do ourselves. What you do is you go to some people who will sell you like purposely built security hardware, so eventually they will sell you a specialized, super expensive firewall. But eventually that fails as well, because like the problem is the attack scales horizontally, so there'll still be like more malicious users appearing on the internet and like sending traffic to your endpoint, right? And basically even the most expensive firewalls kind of get overloaded, and then nothing works anymore. So this is like the first problem of distributed attacks, that like typical distributed attacks scale horizontally. How do they work? Let's say people find a vulnerability in some kind of IoT device which is used all across the world, and then the attackers basically like take control of these devices and start using them for malicious purposes. So basically acquiring a computing resource for attackers is quite cheap, and they can do it all across the world. But if you go to the path, like just buying expensive, powerful gear to handle all of this, you're kind of scaling your defense vertically. And this is like I mentioned in the previous talk, security is an arm race, but if you do go that path, you will always lose that arm race because it's always cheaper for an attacker to get more resources, and it will exponentially more expensive for you to scale vertically to protect from some attacks. So the one thing you can take away from this talk is that if you want to efficiently protect from global distributed internet attacks, you actually need to build some kind of global distributed defense. So your defense needs to scale horizontally as well with the attack. And this is like, for the rest of the talk, I will be describing how we did it in Cloudflare, our concept, and what things you can look into it. So let's start with the network itself. Who here is familiar with internet addressing, how it works? Well, many hands. So like typically, most of us use unicast addressing, right? So you have a resource somewhere on the internet, and it has an IP address assigned, and via this IP address, our users can kind of find our resource, and traffic can reach our server, right? How do we build, from this type of addressing, how we build a system which is scalable? Well, most of us, what we do, we kind of like do a unicast with load balancing. So we put that public address, IP address on some kind of front entity, right? And then we have a bunch of backend servers connected to it. So the heavy work processing is done on the backend service, and the front-end entity is kind of receiving this internet traffic and like distributing across the backend services. It kind of works, so you can reasonably scale your infrastructure by adding more backend services, but like this front-end service still becomes like a single point of failure eventually. And this is not a good example of internet scalable approach because it's just same unicast with load balancing. So who here is familiar with anycast? Oh, a couple of hands. So anycast is different, right? So what anycast means is just we have our public IP address, but we have several entities across the world sharing the same IP address. Is that a mistake? Well, it's totally legitimate from the internet's point of view. And basically, the way how internet was designed many, many years ago, that if you do that, kind of your users, if they want to reach your resource, they will be more or less well routed to the closest presence of this IP address. They, like in the internet, you can take many different traffic paths, but you will eventually take the shortest one or compute effective one, depending how the internet is how the network is configured. And the good thing about it, it works both for users and for the attack traffic. So if you hide your resource behind an anycast network, it's kind of like eventually naturally distributes all attack traffic across the world, like as many anycast points as you have. So this is a, map of Cloudflare data centers today. I don't know if it's very accurate, but the gist here is like we have a lot of data centers and a lot of servers, and this is all like an anycast network. So it's very hard to attack such a system from a global point of view because traffic will be somewhat evenly distributed across all of the world across this network. Yeah, so the good points about it that both user traffic and attack traffic are distributed all over the world. And in this schema, you see we never need to use any specialized security hardware. We just like naturally distribute traffic with no specialized concept. We use the natural concept of the internet, how it's supposed to be used. In this system, we have incremental costs in adding more capacity to handle more traffic. Just spin up a new data center, add more servers to an existing data center, and like the traffic will eventually, part of our traffic will eventually flow there. And like this gives us the ability to truly horizontally scale our system, not only for protecting ourselves from large distributed attacks, but actually serves more users. So you horizontally scale, you can just service more users because you eventually can serve more traffic. Now let's talk about the internet hijacks and autonomous systems and BGP. So who here think they're older than the internet? A room of young people. Yeah, so what is the internet? How internet works, right? So internet is actually a collection of, a network of networks. It's and in internet terminology, we call these networks autonomous systems, and they're usually designated by a number, AS, and some kind of number. And these autonomous networks continuously exchange traffic between each other. But how do you know, like, let's say, like AS1335 is an autonomous system for Cloudflare, for example. But if some users want to access a resource on Cloudflare, let's say 1111, how does the internet know where to send this traffic? And the underlying pillar of the internet is a border gateway protocol. So what these networks basically do, they continuously announce to the world which IP addresses they own. So like, or CIDRs or whatever. So, and other networks receive those announcements and they kind of know to which autonomous system to send a particular traffic destined to a particular IP address. The problem with that internet was designed like how many, more than 50 years ago, and it was based on some kind of gentleman's agreement, and because you just, like somebody announced, I have like this, and everyone else just believe them, right? Like, yeah, you have this IP address, here's your traffic. And in modern days, like people realize that you can become a malicious entity on the internet and start announcing IP addresses which you don't own, basically, and start getting this traffic. So the modern way to solve this problem is that like with an upgrade to the BGP protocol, you have the modern way to sign your announcement, and basically if you start signing your announcement, but it's kind of a team sport, right? So like people who own some IP resources, they sign their announcement, and people who actually send the traffic, they have to only send it to the announcement they cryptographically verify. But if you agree on this system, well, basically it allows us to kind of like send traffic only to legitimate autonomous networks, and thus like blocking out an attacker completely. And this not only helps security, actually. There are tons of announcements on the internet just due to network gear misconfiguration, and sometimes when you have bad connectivity just because of that. And like the RPKI, which is a modern technology to sign your BGP announcements, it kind of really helps even on with performance on the internet, because the misconfigured routers do not like send traffic to misconfigured endpoints. But again, as I mentioned, it's a team sport, so you need networks to sign their announcement, and you need other networks to actually verify those signatures. Unfortunately, not all networks are currently doing that, and we actually developed a tool to see if your current ISP is actually verifying the BGP announcement. And the screenshot on the right, left, whatever, with the red one, I just took yesterday from my hotel Wi-Fi, and unfortunately it's prone to BGP hijacks, but like some ISPs are doing it properly these days, and more ISPs doing it properly. But if you have the leverage to select your ISP provider, just double check if they support BGP and RPKI, and like if they don't, make sure to reach out to them and ask them to do so. So let's talk about CDN bypass and egress tunnels. So who here actually use some kind of a CDN service? A couple of hands here. I mean, to be honest, with modern applications and like it's very hard to be online without a CDN, just because we have so many users and it's so much more efficient. You can cache content and many other stuff, and CDN can also provide you with some security concept. But there is so eventually how it works, you have your resource, again, on the internet. You put it behind some kind of CDN. It can be Cloudflare or any other CDN there is. And basically how it works, instead of connecting to your resource, users are connected to the CDN. But CDN being this middle layer between yourself and your users allows it to provide like more add-on services. So one of them can be like some security firewall, where the CDN will allow your users to access to your resource, like it will proxy users' request to your resource, whereas if it detects that the request is somehow malicious, it will not pass through. There is a flaw in this design though, and the problem is that with most CDN setups, basically your service is still internet routable. So the way how you configure it, like the CDN will hide your real IP address, but your resource is still on the internet, and CDN actually uses your IP address to proxy the request to the users. And if the attacker somehow learns that internal IP address, they can just bypass the CDN and start sending traffic directly to an IP address, and rendering the protection of the CDN useless because it just overloads your resource, and CDN can do nothing without your resource. So to cope with this problem, there is a new solution now where, well, what if your resource is not internet routable, right? So if no one can reach you from outside of the internet, you just run your stuff on localhost. Kind of works, right? But then you can configure that your server can still have like outbound internet connectivity. So what it can do, it can establish an outbound connection, a tunnel to the CDN, and then basically when users and legitimate users connect to the CDN can use these already established connections to proxy their request back to your resource, but technically the attackers will not be proxied because CDN will block them. But the nice thing about it, the bypass is now impossible, because if the attacker wants to bypass the CDN, they don't have any internet routable information to actually reach your service, which kind of gives you enhanced protection. All right, so now we talked about how to protect yourself on internet scale, but this is only one layer, right? So let's now zoom into a data center. So in this design, apart from like outbound connections and BGP hijacks, we actually never filtered attack traffic and blocked attack traffic. We just distributed it evenly, not allowing to overwhelm our system. So what can we do on the data center? So in this case, if we do that, the data center still receives both good and bad traffic, right? And traditional design, again, inside the data center, and to be like somewhat horizontally scalable, is like you build the load balancer and a couple of backend servers. But again, if there is too much traffic coming to a single data center, your load balancer becomes a single point of failure and can be overloaded. And again, you can replace it with a more expensive and specialized load balancer, but you're kind of following the same path between like horizontal versus vertical scale. What you can do instead, you don't have to use a load balancer. What you can do, in your data center, you already have a router, right? So you can just use your router. And in this design, kind of like your load balancer has your publicly internet routable IP, but you can replace it with a router and not put your internet IP on the router. Instead, you can put this internet IP address on your servers, and servers can use a protocol called ECMP to talk to your router. ECMP is in data center variant of BGP of the internet. So it's kind of based on the same announcement. So you kind of announce to the router from your server, then yes, I'm a server and I have these IP addresses configured, and if the router receives those announcements, it will send part of the traffic to your server, some part. Right? And in this design, it's very easy actually to horizontally scale inside the data center. So if you just need more capacity, you just add more servers. They might be configured with the same IP address. They start announcing their IP addresses to the router, and router will just start distributing traffic to those servers. And it's actually very easy to put servers out of service for maintenance, because if you just shut it down for whatever reason, even if it crashes, it just stops announcing, and the router will not be sending any traffic to that server. So again, we build a Inside the data center, we build a horizontally scalable system to distribute the traffic without any expensive gear, specialized load balancers, and whatsoever. All right. But in this design, again, we are not blocking the attack traffic. We're just building a system to continuously redistribute and redistribute, redistribute. So even in this design, your server still receives both good and bad traffic, right? So let's look into how do you actually protect from bad traffic on your server. Who here knows what this does? Yeah, so this is a firewall rule for Linux to block all incoming traffic. Do you think it's an effective protection from bad traffic? Well, like in extreme cases, yes, right? Because kind of like, yeah, you will be blocking good traffic, but you won't be getting any bad traffic. But is it a good solution? Well, no. Turns out, like, even if you block all incoming traffic on the server with an amount of capacity from the attacker side, they can still overload your server. And why is that? Well, this is how basically packet processing, like the network stack, works on Linux and actually on any other inferior operating systems like Windows or Mac OS. So your NIC receives your packet, right, when either good or bad traffic goes. So what the NIC does, it sends a hardware interrupt to the main CPU, to the operating system, and then there is a network driver which usually receives those interrupts. So what happens here, to actually process that packet, Linux internally allocates a data structure called SKB, stands for socket buffer, but it does some memory allocation, copies that data from the packet to that structure to actually process it later. And then the driver needs to do it fast and just re-enable interrupts back so like the system is responsive. So after that SKB is created, the driver sends this SKB to the operating system layer 2 implementation, where the layer 2 of the operating system does some kind of processing. It checks if the MAC address corresponds to either to your network card or kind of like the MAC addresses you're allowed for the system to receive. Yeah, so it parses layer 2 headers, calculates layer 2 checksum. It can merge frames for better efficiency, so like 2 consecutive packets and can merge to 1. So yeah, it does still some work, and then it sends it to the layer 3 protocol. And what layer 3 protocol implementation in the operating system does, it again parses layer 3 headers like IP addresses, does maybe generic receive offload, connection tracking. If you configure the firewall, you can use that in Linux. It does layer 3 checksum calculation, calculates the routing information, so if this packet is designed for local system or should it be routed somewhere, etc. And then if you hit that firewall rule, it will actually drop the packet. So the problem is with enough incoming traffic, the system can still be overloaded because for each packet, even before you drop it, the system has to do a lot of work. And we kind of proved it actually practically with some tools like HPing, that you can actually overload a server, a CPU on a server, with a firewall which blocks all incoming traffic. So the technology we use to protect here is called XDP, which stands for Extreme Data Path. Who here is familiar with eBPF in Linux? Some hands. So yeah, eBPF is a new shiny framework, sorry, for Linux to do basically everything from performance evaluations to security and like a sheer part of programming networking. So what it does is it allows you to write small programs in a somewhat limited programming language, extended BPF, and which does stuff, right? And within XDP, yeah, so and the idea behind eBPF, it's very fast. It's programmable, so you can write somewhat very complicated filters and programs in this language, and it's safe. Even though it works, it's another program which you insert inside the Linux kernel. It's designed in a way that you can never crash your system even if you write a bug in your problem. Like basically the verifier will never accept and not allow your program, this program to be loaded if it considers it unsafe. And it has really great documentation. So within the express data path, you can actually write very complicated filtering rules in eBPF language and insert it very close to your networking hardware. So in this case, if we go back to our traditional design, you can actually filter traffic with customized eBPF programs, either on the driver layer, like even before it reaches the layer 2 in your operating system, or even more and more network cards now are supporting eBPF natively, so you can even run programs on the network card itself. So technically you can write firewall rules, insert into your network card, and your network card will process the packets very fast, and it will never send you bad packets to the operating system, not even generating an interrupt. And in this case, you can really filter loads amount of attack traffic without overwhelming your system, because you skip doing all this extra work. So, and in Cloudflare, we build a whole concept, complex system based on this. So like, again, we go back to our network. We have all these data centers across the world, and they continuously send sampled traffic to our central processing engine. And that central processing engine is kind of programmed in a way it can decide how a good or bad traffic looks like, and for bad traffic it continuously generates and adapts new eBPF filters and distributes them to all our data centers. And also for a faster feedback loop, we kind of have a localized in-data center processing capability as well. And the good thing about it, if we detect an attack in one of the data centers, at some point while the system learns its characteristics, attack may go through a little bit, but eventually our local data center will, this entity who designed these eBPF programs will learn how to block that bad traffic, and it will be blocked. But the nice thing about it as well, it will send that information through the central engine and distribute to other data centers. If the same type of attacks arrive at other data centers, it will be already automatically blocked. So this kind of allows us to build a network where everyone is kind of helping you. Like if one of our users detect a bad traffic, so all of the users are protected because they kind of benefit that we learned how to mitigate that attack. Okay, so we talked about internet layer protection, data center layer protection, server layer protection. What about the application layers, right? So I didn't have to go very far. I just went to my spawn folder and found this, that I1 and M1, right? And if I click on it, there is a nice PDF. Luckily, Google tells me that I shouldn't click it, but if I didn't, I might have clicked it, right? So, and this brings us to phishing attacks. So technically, you can click on the PDF and infect your systems, and this is your computer, and you're running like a bunch of applications, and if you click on a bad link, you might actually, get infected, and your application get infected, or your browser session get infected in best case. In the worst case, it can actually go out and infect all other applications or even your entire system. So what is a good solution here to protect? Well, maybe don't run anything on your computer, right? So you'll be safe. Well, yeah, but it's not very practical, so you can technically run your application in some kind of sandbox, but eventually there are still, again, security is an arms race. There is sandboxing techniques are continuously evolving, but actually there are more sandbox escapes are being designed as well. So for safer things, at least for the web, we have a system called remote browser isolation, where it's basically don't run your browser on on your local machine. So instead of running on your local machine, you can run it on some kind of outside infrastructure, which creates these various sandbox browsers for different users in very constrained sandbox environment, and even if you click a link in that environment, malicious link, and one part of the environment gets infected, it kind of then will be shredded away, and it will not affect any other sessions on the infrastructure. All right, I mean, this is all I wanted to tell you for today. So here's some conclusions is, basically, to protect from global distributed attacks, you need a global distributed defense, and like vertical scaling will fail eventually, and don't be fooled to believe otherwise. The network is the computer, and the internet is now your security perimeter, and basically you can't be designing like internal and external networks anymore, like building firewall rules, building security based on firewall rules based on IP addresses, because everything runs in the cloud can be anywhere, and anything both legitimate and bad can connect from anything. So like firewalling, security by firewalling on the network layer is not very efficient anymore. You need like better identity checks, zero trust, and other stuff. And do practice defense in depth. So like as you saw, we need to actually build an effective defense. We need to think on each layer, both inside the network stack and in the application stack, and bless you. And, and that means I'm right? Both on the application stack and the network stack, as well as like on internet layer and like your server layer or service layer. Thank you very much, and I think we still have some time for questions. Any questions? Sorry. Yes, please. I'll shout it back. So the question was, the traffic filtering layer, how do we decide what is good traffic, what is bad traffic? So unfortunately, it's an arm race. So the system which does it is kind of like, we have been building it from the beginnings of Cloudflare, and it continuously evolves. So first it was some basic heuristics, even with some manual input, like if a user reports an attack, we kind of like know it's an attack traffic. Eventually, like when these huge botnet attacks started appearing out, we kind of built a system to learn the characteristics of it. And the nice thing with eBPF, you can actually analyze packets, not like firewall layer, like you only do it like on the network information, but we can also go inside the data and like see if this user agent doesn't exist or other stuff. Now we're kind of ramping up our AI capabilities, so it's kind of it's a mix of like heuristics, various things, and AI. So it's kind of done naturally. So let's say, for example, there is levels of traffic which are not expected from some workloads. So it's simple to visualize. If you have a dashboard and you're normally like doing like 2,000 requests per second, and suddenly you're doing like 1 million. That's probably an attack, unless you're a ticket master and selling events to Taylor Swift or something like that. So yeah, it's a combination. It's a complex system, and it continuously evolves. But I guess it's still more efficient than anything because it generates those eBPF programs. Yes, please.
Hello.
Yeah.
Yeah. How do you load balance multicast data centers? If you're relying on the internet to just route traffic from users to the nearest IP address, the nearest data center, and you have multiple data centers, one idle and one nearly burning down, how do you load balance that?
So original Cloudflare design was just purely based on Anycast. And yeah, the traffic goes to the most nearest data center. We do have like a collection of tiers of data centers, so larger ones and the smaller ones. let's say if a smaller one can be overloaded sometimes, we can technically shut it down, and then the traffic will naturally distribute to larger data centers, which not that close, but not as far. Over time, we also build like a more sophisticated system, so now we're not a purely anycast system, we're doing different, we kind of like both anycast and DNS based, so we can actually actively steer traffic to the correct location. We have developed an internal system. There is some public blog post about it, but no code yet, called Unimog and Plurimog, where the Unimog is a data center equivalent and the Plurimog is inter-data center equivalent. So this is like an internal layer 4 load balancer, which allows us to steer traffic inside the data center. Let's say, even due to ECMP, sometimes a particular flow may end up on one server and it's very high load. It can overwhelm it, so like Unimog then can redistribute that traffic across several servers. And same thing happens on the global scale, where if data center receives too much particular traffic and we just don't want to drop it, but services elsewhere, we can direct a particular type of traffic or like a flow to another data center for processing. So it's also actually based on eBPF and XDP. So we're all like eBPF, XDP shop.
You touched on DNS briefly. I always thought back in the day, Cloudflare might have using sinkholes to suck in bad traffic. And I was curious, what you described was more like, we're going to keep accepting it and dropping it, but did you have any machinery that, right, we've identified this traffic, we're actually going to take it away from a bunch of servers and just sink it into a black hole? Is that a mechanism used? Is that part of your routine internally? And do you use DNS?
We used to do it in the past.
Yeah.
Now we also use some other previous technologies, which were like XDP is quite recent, some more proprietary solutions from like the network hardware we bought, but now we just don't have to. So technically, the way even with the largest attack, the way how we distribute traffic, and like if we come up with proper XDP filtering programs to drop it on the server, we don't need to use any routing to actually black hole the traffic. So servers can reliably like drop enough packets.
They drop faster than you need. Okay.
Yes, yes.
Hi, thanks. I'm curious, what does Cloudflare do to protect itself from CDN desync events like what happened to GitHub a couple of years back?
Sorry, I didn't. Can you repeat the question?
I'm curious what Cloudflare does to protect itself from CDN desync events like what happened to GitHub a couple of years back.
Can't really. From CDN desync?
Desynchronization. And so what happened with GitHub a couple of years back was one of their data centers kind of dropped out for a short time, became out of sync with the rest of the CDN. And then in trying to bring it back up, it started to block the DCN network updates and prioritized user updates, which meant it kind of got out of sync with the rest of the network in its own way, as well as falling behind from the rest of the network. So it was like a two-way desynchronization that happened that required a couple of days to manually unpick it. I'm curious what Cloudflare has in place to protect itself from that single point of failure type thing.
You mean, let me rephrase the question and you tell me if I'm right. So like when we put out the data center of a production, it kind of desynchronizes from the rest of the internet, right?
Yeah.
And when we put it back in, there is like a timeline where we need to synchronize it back with the current state.
Yeah.
Yes?
Yeah.
Yeah, I mean, we have a system called like a distributed key value store, which we kind of use to distribute all our configuration, and it's been designed in a way that it can kind of like replicate a particular small settings within seconds across all over the world. And obviously when we kind of put the data center back online, there is a brief period where we, so like the data center is already online, but the routers are not doing BGP announcements yet to the internet, so the traffic is not received. We wait for that internal distributed key system key value store to synchronize, and when we continuously monitor the lag, and when the lag is like very minimal, we start announcing. So it's kind of part of we have like a pre-online checks which we run through before putting the data set.
Good to know, thank you.
Cheers. I had a question about ECMP in the data center.
Yep.
I think you said that using the router to distribute traffic eliminated the single point of failure from a load balancer.
Yes.
I don't understand how a load balancer distributing traffic is a single point of failure and a router doing the same thing isn't.
Well, load balancer, like, again, we're talking about in the concept of you don't buy expensive network gear. So if you put like a dedicated server as a load balancer, it will not be as efficient as a typical router, because router can switch packets on a line card where like a regular server like load balancer will not have it. So technically, router can do it much more efficiently to distribute a flow between a bunch of entities than a load balancer, if that makes sense. And again, with a load balancer, you're kind of prone to the same error as I showed on the server. So let's say you have several backends to load balance the traffic. They have to traverse the network stack of the operating system of the load balancer, and it needs to do a bunch of work. So if you have a very big volume of incoming traffic, you can technically more easily to overwhelm the load balancer than a router, which just does it on a line card, which is an ASIC or something.
Thank you. And one other question. Does Cloudflare ever null route customers who are getting too many bad packets?
No, not anymore.
How do you manage that?
As I mentioned before, we try to just filter out the bad traffic, and we try to service every connection. And like if we can filter we don't have a need. Like our capacity can cope with the biggest internet attacks, so we don't have the need to null route a customer anymore. So if we can effectively just drop packets on our servers, which are correlated with a bad attack traffic, we just do that.
Okay, cool. Thank you.
Okay, I'll leave 2 minutes for the next speaker to come up. Thank you very much. Talk to you later.